Hello, everyone. Good afternoon. My name is Ali. I'm coming from Turkey, here from Özyeğin University. I might be the only academician here in this meeting, but hopefully the things I'm going to explain are not going to be that boring to you, because I do consult for Comcast, and then prior to that, I consulted for a number of other companies. I try to do applied research, which makes my research relevant, and then it keeps up to date and all that. I have a number of grad students working with me, and then we work really on interesting problems. So today we are going to talk about low latency, and then obviously low latency has been part of this community for a long time, and then hopefully I'm going to give you some of the latest results we have. All right, and the slides will be on my website if they're not going to be available from Dmax right away. Okay, more than 50 years ago, 1969. Man landed on the moon, right? Whether you believe it or not, that's the story we are told. So that was the single largest broadcast event in the entire history. 650 million people. Even my parents remember that. Obviously, I wasn't born at that time, but they said that they were in front of the TV watching the whole event, right? And then these astronauts on the face of the moon, they use this primitive antenna. They sense audio and video signals to the entire world under less than 3 seconds, right? And then that was about 250,000 miles, which is really quite a distance, right? 50 years forward, Super Bowl 53, and then lots of technology improvements, 8K cameras, augmented reality, a lot of things that you can even, you wouldn't even imagine 50 years ago. And now from the stadium in Atlanta to maybe a subscriber like 5 miles away from the stadium, the latency was about 45 seconds. Obviously, that's not really much of a technological advancement, right? So what's really happening here? Something must be wrong here, so that we are not really able to keep up the latency that we were able to have many years ago. So today, if you look at all the premium support services around the world, and I live in Turkey, there are a lot of premium sports, especially soccer, not football. And then in Europe, right, it's a lot of football over there too. But then Olympics, NBA games, NHL games, whatever you can think of. You look at all those sports, there's literally almost no low latency offering today, just except maybe Prime Video. I know that there are some Prime Video guys over here. Kudos to them, right? They try to offer low latency for Thursday night football. But if you look at Apple TV services today, none of those baseball games are offered at low latency. So why are people still scared of doing low latency? We developed the low latency extensions for Dash, and then Apple did a few years later, almost 4 years ago, right? And something seems to be wrong over here. So when I'm talking about low latency in this talk, I am actually referring to the column in the middle. It's not like the near real-time latency stuff. It's not the ultra-low latency stuff. It's really the low latency stuff, like 1 to 10 seconds. You want to be your OTT service on par with your broadcast service. So if I am watching on my cable service versus OTT service, I would like them to be more or less within the same time frame, within a few seconds, okay? So that's what we are really focusing on in this talk. So latency, as you know, it is glass-to-glass latency. That's usually what we care about, right? From the source all the way to the players, right? There is a camera, contribution encoder, distribution encoder. There's a packaging process. There's an encryption process. And then there's an origin, ingest, and then through the CDN, you reach out to your players. Now, there are a lot of things happening, obviously, right? And sometimes the content is just coming from a satellite feed or a cable feed or IPTV or another source. So you just get the stuff into your OTT workflow and then distribute it over the CDN. And that's what we call as OTT latency. If it is from the source to the player, it's end-to-end latency. Now, there are a lot of factors that come into play that will increase your latency, right? Encoding pipeline. It's going to take several hundreds of milliseconds, if not seconds. And then packaging ingest, as I said, server I/O, license, DRM operations. You need to fetch the keys and all that stuff, decryption. But again, in this talk, we are just talking about playhead positioning and the playhead behavior in terms of rate adaptation, how we are going to size your buffer, how we are going to play out your content, and those things. Otherwise, there are other places where you can actually optimize the latency. Now, I started working on this problem 4 years ago, just when we were starting to develop the low latency dash extensions. So at that time, obviously, there wasn't really much, many services out there. And again, today, unfortunately, there are not really many services out there anyway. So Twitch, we collected a lot of data, months of data from Twitch. I'm gonna show you some results over here. Maybe you have seen this slide before if you have attended one of my previous talks, but this is data, streams coming from Twitch to our computer, and then they go through a proxy where we emulate the network, and then we try to understand what the Twitch player is going to do. This is the bandwidth regime that we are applying to at the proxy, and then these are the segment throughputs and the segment requests made by the player. Now, as you can see, we increase the bandwidth, we lower the bandwidth. There's really not much change. The player keeps stalling, but then it is really stuck somewhere in, at 1.8 megabit per second, something like that, right? This is not really right. This is not how ABR works. This is not how it is supposed to work. And then we actually found out a couple of other services, and then we tested them as well. And then we realized that actually many of them, when they were in the low latency mode, they weren't offering multiple bit rates. They were offering a single bit rate because they couldn't make rate adaptation work. And then, we said, okay, this is an interesting problem, so we should really solve this. And then this is a paper we published in 2019. This figure explains it clearly, but I'll break it down for you quickly. So there's a real-time event you are capturing, and then, each of these blocks, different colors representing different segments, and then each of these blocks are representing a CMF chunk. It could be one frame, it could be multiple frames, doesn't really matter. So as you produce these chunks, you are outputting them from your encoder and packager. And then, once the segment is over, then you continue with the next segment. A non-low latency client is going to make a segment request. It's going to get the whole segment once it's available. A low latency client is going to make a request. It's going to get this segment, which is still being generated in chunks. It's going to get the lump sum for all the chunks that are available at the moment, and then the remaining chunks are going to just flow. Now, if you look at this workflow, what's going to happen is that in the first case, the client can actually make a good estimate of the bandwidth because it's going to be segment size downloaded by segment download time divided by the segment download time. It's going to give you a good estimate of the bandwidth. But in the other case, it's not because there are a lot of idle times between the chunks, and then that will actually lower your estimate, and you will never be able to actually, predict the bandwidth available in the network. Now, once you know the problem, you can actually come up with a solution, and we did. This is a paper, follow-up paper we published later in the year, and then this method was called ACTE, ABR for chunk transfer encoding. Okay, so we do bandwidth measurement. It's a sliding window of the bandwidth measurement for each chunk. And we know how to identify the chunk downloads in a messy buffer. The paper has the details. And then we do bandwidth prediction. This is really the critical part. You don't just measure it, but you also try to predict it for the future. And then you do your rate adaptation based on that. Once you know what the throughput or the bandwidth is going to be, then you can make a proper rate adaptation decision. Now, Guillaume mentioned this. And then right after we published this paper in the following year in the ACM Multimedia Systems Conference, I am very, I was very happy to see that, John Bartos over here and then his colleagues from Twitch, they sponsored a grand challenge on this low latency stuff. Twitch was obviously, working on this domain, and they wanted to see, what people from the academia, universities, and then research organizations could actually come up with. So there's a blog post here. I believe Guillaume's presentation is still included, but here is a blog post. And then there's actually a YouTube video, which includes every finding from Twitch guys. Now, if I can change my slide. Yes, so what the challenge was, yes, keep the latency around 1 second. That was very aggressive, actually. And then balance the other quality of experience metrics, like stall duration, stall count, the streaming bitrate, resolution, less bitrate switches, a number of things, right? We had a formula at that time. And then the approach for that challenge was, yes, we should do bandwidth measurement. We should do a proper one. And then we should do bandwidth prediction, if we can. And then we do rate adaptation, in which case many of the solutions were actually based on machine learning. And then adaptive playback, which also a couple of solutions included in their solutions. Adaptive playout mechanisms. So measurement, smoothing, and prediction. A lot of people get confused by these terms, so let me explain them briefly. So you can make a measurement. You can make an inaccurate measurement. You can make an accurate measurement, but it's just a measurement. And then these are your raw samples. And then there are some ABR schemes out there that use only these raw samples. And then you can run actually a smoothing algorithm to get rid of some outliers and that sort of thing. And then you can come up with a smoothed value for your bandwidth value. And then there are ABR schemes out there, which DashGS uses today, throughput-based. That's based on that. And then there is prediction step, not just for the next step, but maybe the next 2 steps or next 3 steps is just your prediction horizon. And then you can, use some computational intelligence techniques to actually, compute what the bandwidth is going to be in the next second, in the next 2 seconds, and so on. And that's what we are going to talk about today. So there are also a couple of different smoothing algorithms and different ways to measure the bandwidth. I'm not going to read all these items. You can quickly look at them. SWMA, a sliding window moving average, harmonic, exponential weighted moving average, and then probe, which is Will Lowe's famous approach, right? You use an external data or previous segment to download some stuff from the CDN to figure out what your bandwidth is. And then segment, last downloaded segments based on, bandwidth based on that value. Now, we compared all these different methods, right? And then this is what really happens. Obviously, this is just one example, so don't take it that, this is always the case. So this is our throughput diagram. This is the actual throughput, okay? This is what the SWMA algorithm gives us. This is what the harmonic gives us. This is what the exponential weighted moving average gives us. This is what probe gives us. And this is what SLBW gives us. As you can see, the prediction error is quite significant from one algorithm to another. Yes, for a different bandwidth trace, the amount of prediction error could be different. If you have a large prediction error, obviously you are not going to have a good ABR strategy, and your client is going to fail really miserably. Now, if you run the smoothing algorithm in a couple of corner cases, you see really interesting things. And then Mark from Akamai alluded to that point in his presentation too. So if we let the client do not any rate adaptation, so there's no rate adaptation, but it just uses exactly the same bitrate the content was encoded at different bitrates over here, as you can see. And we kept the limit at 5 megabits per second. This is what the client can actually measure. So if you don't let the client upshift, if you rate limit the bandwidth, the client will never be able to upshift to a higher bitrate. Even, it's because it cannot even measure that kind of available bandwidth. So this is really a bad thing because the client cannot really measure, how much data is available until the pipe is actually fully full. Now, in the second scenario, we let the client do rate adaptation, but there is still a cap in the system, and then this is how over time it's going to progress to the optimal bitrate. So it's going to upshift, but not necessarily it's going to be a very fast upshift. Obviously, it depends on how aggressive your exponential weighted moving average is. But in this case, by the default values, it takes like 80 seconds for the client to upshift to this value. Now, those are some obvious problems. Now, can we fix them, right? Everybody knows about these problems, and then we have known them for a while. So what can we do to fix these problems today? And that's when my students and we thought we could actually collect a lot of data and grab some existing public data sets, train a number of models, right? And then feed this into the ABR and see how it works. This is exactly what we did this AMP player, okay? So we have data sets that are available, as publicly in our paper. We trained the data, and then we built a number of prediction models. As you can see, we have 7 different models. 2 of them are statistical, and 5 of them are neural networks. There are different types of networks, which I'm not going to get into, but they have different advantages and disadvantages when it comes to implementation. On the client side, the client tries to understand which model is going to work better for it, and then it will do prediction based on that, and then out of that prediction, it will do rate adaptation. Now, how do we actually model quality of experience? That's a very important question, right? A couple of presentations already talked about this, and then obviously I don't have the exact answer to this question, but our research has also shown that there are a lot of factors that actually come into this equation. So QoE is a function of a number of things, a lot of things, right? It's bitrate, resolution, stall duration, stall count, stall frequency, right? Your playback speed, how far you are from your target latency, and then a number of other things, like the audience type, content type, super resolution techniques, your scalar performance, and all those things, right? So some of those things we will never be able to model accurately. But for other things, we can actually do a pretty good job in terms of, again, machine learning tools. Now, we implemented all this stuff in DashGS, which is the primary reference player that we work with. Obviously, it is extendable to Shaka or any other player too. But I am also heavily involved in Dash Industry Forum, so that's why we pick DashGS as our development platform. And these are the blocks we developed for DashGS. So we have any bandwidth measurement module and then bandwidth prediction module. This wasn't there. It was, bandwidth measurement was there. We just modified it. This is brand new. And then ABR decision can use any of the existing ABR schemes, or you can write your own. And then here you go, right? So the advantage over here is that if we use our own rate adaptation algorithm, which is based on this prediction algorithm, we can improve the prediction accuracy by 50%. 50% sounds like a big number. Obviously, it's not going to translate to a magical QoE improvement. In this case, it's like 40%. And it's a hybrid formula, as I said. But again, you need to look into the details, like is it really the stall count that you reduced, or is it the stall duration you reduced, or you improved the bitrate quality, streaming quality, or whatever, right? It's a number of things. Now, if you do a better prediction, you will hopefully not overestimate the available network speed, so you won't really make really stupid decisions. Now, I know that there are some people in the audience that might be asking, machine learning in ABR is not really a new concept. Yes, it's not new. There are a number of them, OBEO, Pensive, MPC, a number of them have been published before. But with better prediction built into those, we can improve their performances too. So the paper has all the details. I'm just going to say that Pensive and MPC can be improved up to 10% as well. Now, we responded to that grand challenge that was organized by Twitch with our LOL, low on latency solution. And then Twitch guys gave us a lot of useful feedback. We were the runner-up. We couldn't win the grand challenge. We were the runner-up. Then we fixed a lot of issues and then came up with LOL+, which Guillaume showed some results for. Now, this algorithm has this throughput measurement from this AMP player. And there is another statistical model and then learning-based model here, self-organizing maps. And then there is automated weight selection, in which every node actually represents a different QoE factor, so that you can optimize your QoE factors. If you want less stalls, you can increase the weight for it. If you want a higher bitrate, you can adjust your player for that purpose too. Now, this player can do, again, automated weight selection for you, supports individual QoE metrics, and then there's hybrid playback speed, which I actually spoke about last year in Demuxed. Now, my argument in last year's talk was, in low latency, we need to support adaptive playback. We need to reduce or accelerate the playback speed, sometimes to just avoid stalls or catch up with the target latency, okay? And certain parts of the content, especially in sports, people are going to pay more attention to that part of the content. So you don't want to really do too many playback speed changes if a lot of people are paying attention to that content. So we need to do content-aware playback speed changes, and that's my last year's talk. But then we improved that algorithm to this year. Again, we published another paper in August this year. It does now automated event detection. So it understands the important parts of the video so that it is sent as a metadata to the player so that the player can use that information to limit the playback speed changes or not do any playback speed changes at all, or you can increase the playback or slow down the playback by 30%. And hopefully the viewers are not going to actually realize the difference. This is how we did it. We used FFmpeg, thanks JB, and we used OpenCV filters for that. I'm going to show you a video here. This is for demo purposes. There is a pool game over here, and then we identify when there is action, if there is a lot of balls moving around. We realize that it's an important scene so that we limit the playback speed changes. If it is not really, the guys are not playing ball, just thinking about the moves and that sort of thing, well, you can do playback speed changes without the audience noticing that. With that, I would like to conclude my presentation. There is a lot of stuff happening in the research domain, and I hope some of that will be transferred to the industry. And then, thank you. I welcome your questions.